All right. Hello, my name is Maggie, and today I'm going to be analyzing some proton NMR spectra. So first, I'm going to be analyzing the spectra of ethanol C2H6O, and then just to show you a more complicated example, I will be analyzing the spectra of aspirin. So let's start off with the spectrum of ethanol. So what I like to do for these problems is I like to start with the integration. So what the integration is the relative number of equivalent hydrogens per signal. So if we start off looking at this 2H signal, we can assume that based on this integration, there will be 2 H's, so most likely a CH2, if you will. It's very nice because the computer will actually calculate this for you, so you don't have to do a thing. You just know when it says 2H, there's 2 H's. So the next thing I like to look at is the number of signals. So if we take this signal, it's a little hard to see because it's a little jumbled, but there are about 1, 2, 3, 4 peaks in the signal. So based on the n-1 rule, which is the number of signals minus 1, will give us the number of neighbors for that signal. I'll just abbreviate with n. The number of neighbors. So using that rule, we can say that 4 minus 1 equals 3 neighbors. So now, based on that, we can get this little partial structure here. We can say that somewhere in our molecule there is going to be the H2 that will eventually have 3 neighbors. Now we can look at the relative location of the signal to figure out what it is. So for these kinds of problems, I like to just have a chart pulled up because charts really help me. And this chart really doesn't have anything that's going to help us a lot as far as a functional group that has that's attached to 2 H's that is in that range. However, we know that electronegative atoms push things up all the way downfield, where this is downfield. So when we look at our formula, we can say, okay, well, there's an O right here, which is a pretty electronegative atom. So we can, guess that somewhere in our molecule is going to be a CH2 attached to that oxygen. So that takes care of 2 of our H's and that O. So now, knowing that, we can move on to our next one, and we can do the exact same thing. First, let's look at this integration. So 3 equivalent protons is most likely going to be CH3. So now we know that somewhere in our molecule, there is going to be CH3. And because this molecule is just around 1 to 2, this is just kind of the alkanes. There's a lot of stuff in there. It's really hard to differentiate. So we'll just focus on the fact that it's a CH3 with 1, 2, 3 peaks. So 3 minus 1 equals 2 neighbors. So that's really important because now we can look at this and say, okay, well, this equivalent hydrogen group has 3 neighbors, and this one has 2 neighbors. So most likely these are going to be connected. So we can just move this right over here and connect those. So now we're pretty much almost done. We only have one little peak left here to analyze. This one's a little hard to see, but this one has one singular peak with 1 H, where 1 minus 1 equals 0 neighbors. So we know that there's only one possible location that this proton can go, and that's right here on the oxygen, because it has 0 neighbors and it would only give you 1 peak. And we can go back to our chart again, and we can, make it make sense because we know that right here between 3, I guess, and, or I guess 2 to like 3.5 will be these alcohols, or I guess that's not like that, but right here between 3 and 5 will be the alcohols. They move around a lot, which would make sense as it's kind of smushed in here. So we know that that is most likely an alcohol proton. And we can go back and, triple check and look and say, okay, this is one equivalent hydrogen group with 3 hydrogens and 2 neighbors. And there's the 2 neighbors, 1 and 2. And then we can go over one more and say, okay, this is 2 equivalent hydrogens with 3 neighbors, 1, 2, and 3. And then lastly, we can look at this guy and say, okay, well, that is a pushed way down field because it's attached to an electronegative atom, alcoholic proton with 0 neighbors. And we get our final structure, which let's clean this up a little bit so it makes more sense, of ethanol. So for this example, we didn't really have to use the spin-spin coupling, mostly because this is a pretty straightforward molecule. However, I have a different example that'll kind of explain what spin-spin coupling is and how it can be helpful in analyzing NMR. So let's look at this structure right here. So when looking at this, we would expect to see this structure right here. And we know that because this CH3 group will be one group of equivalent hydrogens, most likely around 4, so it's attached to this electronegative atom, and we can see that it's right there at 3.9. And then we'd expect that this red hydrogen would be right here, right here, and this blue hydrogen would be right here. But unfortunately, it's not that easy. When we look at the real NMR spectrum, we will see something more along the lines of this. So as you can see in the real spectrum, these 2 signals are going to be split, each into 2. And this is what we call spin-spin coupling. But why does this happen? So if we can just take this example a little further and look at what we would expect, this is what we'd expect. We'd see one peak right here for the 7.25, and one peak right here for the 6.7. And in our heads, that would make sense. But that's if these 2 protons had no interaction, which, as we'll soon learn, they actually do interact because they're so close on that benzene ring, those hydrogens will couple and reflect each other in the NMR spectrum. So this can kind of be explained if you think of the magnetic field, the applied magnetic field, or the B naught, versus the aligned magnetic field that the hydrogen will get off. So this, if we start with this red hydrogen, we know that it can be aligned with the external magnetic field or against the external magnetic field. So up or down. And in this first example, because the magnetic fields are aligned, so let's look at here. So just to show you guys where I'm at. So in this first example, we're going to look at when this is aligned with the external magnetic field, which is right here. So if those 2 magnetic fields are aligned, then the effective magnetic field felt by the blue proton is going to be exponentially larger, which when you increase the magnetic field, you increase the difference in energy between the alpha and beta spin states. And this gives a higher frequency signal and thus a higher chemical shift than would be expected. So because this large effective magnetic field is being felt by this blue proton, the chemical shift is going to be much higher, and it'll shift it downfield, as you can see right here. So now we can look at exact opposite situation. So if the the external magnetic field is aligned with the magnetic field of the hydrogen. If this happens, then this effective magnetic field will be much smaller than would be expected, which would give a lower chemical shift, as you can see right here. So this makes a lot of sense, because if you were to combine these two, you would get something like this, which is exactly what we see. It's like we see the product of those two interactions right there. And because the blue proton can do the exact same thing, it can either align or align against the magnetic field, it will do the exact same thing, and it'll split that red proton signal in two. So this is a really helpful way of analyzing spectra, because a lot of the time spectra doesn't show up like we think it would. So it's not always super clean, but knowing how these magnetic fields interact, we can predict the shape of certain spectra. So moving on to a little bit of a harder example. Unfortunately, in this example, they don't give an integration value. So we're mostly left to rely on the position of each signal. So because aromatic, just as we talked before, aromatic signals are often coupled and jumbled around just because they're all so close, we would expect to see an abnormal number of signals for this molecule. So first, we'll just rely on the location. So we know that we have these three kind of jumbled up spikes. I don't even want to try to count how many signals those are, because I think that'll just confuse us all. But around 8 parts per million. Now, if we look at our chart, around 8 is an aromatic group, which we know makes sense because all of these could correlate right here. So now, if we look at this signal, let me change that code, is a lot easier to read. 1 peak minus 1 equals 0 neighbors. And that's a big peak, and we don't know the integration, but we can assume that it's a big peak, which means there'll be multiple equivalent hydrogens in that peak. And the only part of our molecule that has a large number of equivalent hydrogens with 0 neighbors is right here. And that makes sense. And then the last peak right here can be correlated with this guy right here. And that makes a lot of sense because we know, based on our chart, that carboxylic acid peaks, the OH from that carboxylic acid will most likely show up between 12 and 9.6, somewhere around there, ppm. And this guy is right there at 11 ppm. So that is how we generally analyze spectra. You can do it just like we did here, where we can match a structure with the spectra, or we can do it like we did up here with ethanol, where we can look at the spectra and we can look at the formula and match the integration and the position of the signals and the spin-spin coupling and the number of signals, and create these partial structures and put them all together in order to create a final structure. So I hope this helps. Thank you so much.